America and Britain are among the first countries to industrialize and release greenhouse gases. They had car engines, steam engine factories since first. Yet there is one glaring problem. Why is it that the first ozone holes were found above Antarctica in the 20th century rather than above America in the Northern Hemisphere? My name is Alex and welcome to my channel, Invisible Links of Science. Here I try to relate daily phenomena in our life to what we study: physics, chemistry, biology, mathematics, geography, and so on. A bit about myself first. I'm someone who gets excited whenever I can apply mathematics to problems in different disciplines, and I want to understand the tangible effects of these different models that we have in our own real life. Today, everyone's stuck at home because of the pandemic. There's one place that I'm missing, and that's the beach. I have to admit that I'm not the type of person to go to swimming classes. I was often the kid on that bench during the swimming classes. I really like watching the waves crash against the rocks and break. An example of those is in those tsunami videos. The World Guinness record of 2020 were the largest waves in the world. What's common in those videos is that in each and every single one of them, we can see that the front of the tsunami falls in front of the wave and it breaks. And that's because the top of the wave moves so fast that it moves faster than the bottom of the wave, and then the entire wave loses structure and it crashes. This is known as the wave-breaking phenomena, and today I'm going to tell you about why it's important. A few things about waves I want to explain first. Number one, what's a wave? So a wave is something that transfers energy and information without actually transferring matter, and this is really important. But how does a wave actually happen? So we start off with a stable equilibrium value, if you will, and some oscillation or some perturbation to that value causes opposing force to act back against the perturbation, and this starts sort of a periodic wave-like motion. When you punch water, the force known as buoyancy pushes your hand back up due to Newton's third law, and this causes the water wave. So that's how a wave forms. Alright. Number two, what do we know about the energy that a wave carries? The energy that the wave carries is directly proportional to the square of its amplitude. The amplitude of a wave tells us the distance between the initial equilibrium value and the maximum possible displacement from that equilibrium value a wave can take. So in the case of tsunami waves, we know it has a lot of kinetic energy because the tsunami wave is so high, and so the amplitude of the wave is going to be so large. So we would naturally expect that to be a lot of energy because it travels very fast. That makes sense. What I want to focus on today is a specific type of wave known as a gravity wave. Not gravitational waves, those are two different things. Gravitational waves are related to special relativity and Einstein and all that. Gravity waves form at the boundaries of two different mediums, for example, air and water. In the case of tsunamis or tides, we see the wind blowing against the surface of the water. This forms gravity waves because that's at the boundary between two different surfaces, and these are the tides. Here's a thought experiment. If we had an infinitely large world with an infinitely large sea and an infinitely large atmosphere, is it possible to have an infinitely large tsunami? Well, we can keep inputting energy into the system until the amplitude increases. Certainly, that's true, yeah. Actually, no, it's not possible, and that's because of the wave-breaking phenomena. The wave-breaking phenomena states that when the amplitude of a wave grows beyond a critical level, it will break, like water waves breaking against the rock. And that's really important because the amplitude of a wave squared is proportional to its energy. So that means all the stored energy of a wave must go somewhere, right? It's actually going to be distributed into turbulent kinetic energy. Turbulence simply means that we cannot predict how the kinetic energy has been distributed. We do not have a deterministic answer to that, so we need to rely on a lot of statistics here. An example of turbulence is in airplane turbulence, I suppose. That's when we have air parcels of different mass and different velocity all colliding together. And the result is basically turbulence because we do not know how the kinetic energy has been distributed in that local air mass. It turns out that gravity waves can also undergo this wave-breaking effect. I'm talking about one type of gravity wave, specifically those caused by the flow of air over mountains. When air parcels reach the elevated rise over mountains, they cannot go through the mountains, so they're forced to rise up. When they rise up, they cool down. As a result, the air particles lose kinetic energy, so the air particle clumps together and it becomes denser, which means that it falls down as a result of gravity. Then it rises up again and it falls down again. So that's a cycle, and that forms a gravity wave. What's important about is that these gravity waves actually propagate and increase in amplitude as they propagate up towards the atmosphere. When they reach just the stratosphere, which is approximately where these gravity waves start to break, in other words, that's the critical point, these gravity waves will break, and they will distribute all this turbulent kinetic energy in the clouds. Sometimes that's why clouds have a weird shape, but they will distribute all this turbulent kinetic energy in the stratosphere. What's important is that in the stratosphere, a lot of chemicals are present in the stratosphere, such as chlorine monoxide, we have bromine monoxide, we have chlorine and bromine radicals as well. These radicals are key chemical reactants in destroying the ozone layer. As a result of this turbulent mixing of the air masses, these reactions get disturbed because the temperature has been mixed between the lower stratosphere and the higher stratosphere due to the movement of air masses. As a result, those key chemical reactions that cause ozone to be destroyed do not happen when there's the wave breaking effects. Even if they do happen, it will be in much lower capacity than compared to when there are no wave breaking effects. Let's take a moment to look at the geography of the world. We know that there are a lot of mountains in the northern hemisphere. We have the Alps, we have the Rockies, and so we have the Himalayas and so many other mountains. Compared to the southern hemisphere, we don't actually have that many mountains in the southern hemisphere, which means that in the southern hemisphere there are less wave-breaking effects. The particular chemical reactions that happen as a result of all these chlorine monoxide, bromine monoxide can happen, which means that the ozone layer will be destroyed. How fascinating is this, that we have geography playing a role, we have chemistry, because, well, atmospheric scientists need to model what actually happens with all these different, so many particles out there in the atmosphere. And we also have, at the very end of the day, physics, which allows for all these chemical mechanisms to happen. I hope this video was helpful. If you guys are confused about anything, go comment down below, and like and subscribe as well. So I'll be making more videos of this type. They're mainly aimed at learning about how what we learn at high school to understand the world are interconnected across different disciplines. My next video will be about how physics is being used in economics. See you next time!